Hi, I'm Ben. Brian and Edward went on vacation, so they left me here to talk to you about Maxima and Minima. First of all, a quick word about myself. I'm actually Brian's older and wiser academic brother. So I empathize with you guys that you have to work with him all the time. So do I. Another quick word is that Audi is the best automotive brand. One might say it's the absolute maxima of automotive brands. With that cheesy segue out, let's actually get started. Quick, what's the definition of a maxima and a minima? If f is a two-dimensional function, or a function on two variables, fy, xy, then the point xy is called a local maxima if f of xy is greater than or equal to f of x prime y prime for all x prime y prime near xy. And similarly, a local minima if f of xy is less than or equal to f of x prime y prime for all x prime y prime near xy. Now one may ask, okay, what happens if, like Audi, there's something that's greater than all other points in the domain? Well, that's called an absolute maxima. So xy is called an absolute maxima or minima. If the respective inequality holds for the whole domain of f. So for all x prime y prime in the domain of f, f of xy is greater than or equal to f of x prime y prime, or in the case of local or absolute minima, f of xy is less than or equal to f of x prime y prime for all x prime y prime in the domain of f. Now we ask the question, how do we find these guys? They're often very important things and have very practical applications. Well, the procedure is actually very similar to the procedure we used to find local maxima and minima, or critical points, in Calculus 1. Recall in Calc 1 what we did was we took the derivative of f, found the places where that's 0, these are our critical points, and then we did what's called the second derivative test. Well, we'd use a very analogous process here. The question now is, okay, what's our analogy for the for the derivative in the multivariable case? Well, that's the gradient. So, first step, xy is a critical point if the gradient of f at xy is equal to the 0 vector. So now we ask the question, okay, what is going to be our second derivative test? Well, this turns out to be the determinant of a matrix called the Hessian. So the Hessian is this matrix. H of f is fxx, fxy, fyx, fyy. Now we care about the determinant of this guy, so I'm going to write d of f for the determinant of the Hessian at the point xy. So this is the determinant of h of f at xy, which is going to be these guys times subtracted from these guys. So this is f xx at xy times f y at xy minus f xy at xy squared, because we're only really talking about functions that are sufficiently continuous so we can exchange the second derivatives. So the third step in the process, we use both the determinant of the Hessian and one of these second derivatives. We might as well pick f of xx. So we compute f xx at our point xy. And now we have 4 different cases. 2 of them where d, the determinant of our Hessian, is greater than 0, and 1 where it's less than 0, and 1 when it's equal to 0. So case 1, d f at xy is greater than 0, and fxx at xy is greater than 0. Well, in this case, xy is a local minima. Right, local minima. Now the opposite, so we still have df xy is greater than 0, and now fxx at xy, let's say he's less than 0. Well then, xy is a local maxima. Okay, so now we have the question, what if the determinant of the Hessian is less than 0? Well, this means that this is a saddle point. This means that at a very, very small level, it looks kind of like a horse's saddle, where part of it goes up, part of it goes down. And the final case is when d of f of xy is equal to 0. And this is our worst case scenario, and we actually don't know what happens. So you either have to compute it directly or find some other more clever way. So this is when the test fails. And we get sad. Thank you very much.